So today I'm going to talk about 3 lessons that we learned from running our stateful streaming pipelines with Apache Flink and Kafka. So before we dive into the technical part of the talk, let me first introduce who we are and what we do, right? So Bloomberg is a company that provides financial news, data, as well as research to the participants of financial markets. Our flagship product is the Bloomberg Terminal, which is a software that delivers a diverse array of information, news, as well as analytics to facilitate financial decision-making. My team specifically, we work on building the infrastructure for our near real-time pricing of fixed income securities. We're actually heavily using Apache Flink and Kafka in our pricing pipeline. So at a very high level, right, our pricing pipeline can be generalized as this diagram down here, where we start by consuming market data information from various sources out there. These type of market data information are made available to us through some Kafka topics. From there, once we get these information, first thing we do is to normalize them. Right? We then use these normalized data to perform pricing of the securities that we cover. From there, once we have the prices, we then enrich these prices with additional fields. And the last step is to send these enriched prices to some downstream Kafka topics where the data will then be made available to our clients by our downstream teams. So the peak market data volume that we're dealing with in this pipeline is often more than 300,000 ticks per second. And within this pipeline, we're using Kafka topics to sort of connect different components, as well as interacting with our upstream teams and downstream teams. And inside this pipeline, so most of the components are actually Apache Flink applications, with just a couple exceptions being C++ applications. So today I'm going to talk about some experience that we learned from sort of developing and maintaining this pipeline in our production environment. So the first topic that I want to talk about here is to always optimize your serialization in your Flink applications, right? So here, let's take a look of this example Flink topology here, right? So this is actually the Flink topology for one of the applications in the pipeline, right? So here, the topology start with 3 Kafka sources, which they each read in a input Kafka topic, right? Each source is followed by a map function. From there, we have a process function that does some stateful processing, and it's using RocksDB as the state backend for it. Once the data is processed, we then send the data to downstream Kafka topics via the Flink Kafka sync. Right? So the topology here is not very complex itself, right? However, what we did not realize initially when we first built this pipeline was how much serializations that's involved here in this application. Right, so generally there are 2 types of serializations that's happening inside this application. There is the serialization that's involved when the application is sort of interacting with external sources and external sinks. So these serializations are marked as green dots here on the diagram here, right? So as we can see, these serializations are mainly happening inside our Kafka sources and Kafka sinks. There is also the Flink internal serializations, right? So these serializations are happening whenever sort of records are being passed from operators to operators or from operators to RocksDB, right? So here, these type of serializations are marked as red dots here on the diagram. So as we can see, whenever 2 operators are connected together or whenever the operator is connected with RocksDB, there will be some sort of serializations that's going on. Right, so for the green dots, right, for the serializations that's involved when the application is interacting with, when the application is interacting with upstream sources or downstream sinks, right? So these serializations are actually done through some user-provided custom serializers or deserializers, right? So there is not much that we can optimize in these sort of serializations. However, for the serializations that's in between of our Flink operators or in between of the operator and RocksDB, Generally, there are 3 types of serializers that can be used here. We have the POJO serializer, which will be used if our record type is a POJO in our Flink application, right? And here, POJO is basically plain old Java object, right? From there, we have the Avro serializers, right? So as the name suggests, the Avro serializers will be used if the record type in your application is an Avro schema-generated type. Last but not least, we also have the cryo serializer, right? So cryo serializers are actually used as a fallback for all other sort of generic types, right? So basically, if the record type in your application does not match with any registered serializers or deserializers, then cryo will be used to perform serialization in this case. Right, so cryo itself, it's a, I would say, very powerful generic serialization framework that works on most of the types out there. However, this comes at the cost of performance, which we will demonstrate next. So here, to demonstrate the performance difference between these different serialization methods, right? So we set up a benchmark application here. And what we want to do is we want to compare the throughput when running this benchmark application under each different serialization method, right? And when running these benchmark applications, they will be executed under the same record type as well as the same Flink topology. Right, so here, let's first talk about the setup here. Right, so on this slide, this shows the sort of data structure or the record type that we will use in our application. Right, so this, so here we have on the left side, type 1 is going to be the record type that we want to use in our application. Right, so type 1 is a nested class. It has a couple of primitive types inside it. It also has a reference to type 2, where it's also a nested class that has some primitive types inside it, and also reference to type 3. Type 3, on the other hand, is just a simple class that has a bunch of primitive types inside it, right? So together, this sort of data structure is going to be what we want to serialize and deserialize, and this is going to be what's being passed from operators to operators. And here's the Flink topology that we're going to use in this benchmarking application, right? So the topology starts with a source operator that's basically keep generating instances of the type 1 class, which we saw from the previous slide. From there, there is a bunch of map operators and process functions followed. And at the very last, we have a sync operator that basically sort of takes in the records and omits them. Right? And for the map operators and process functions that's in between of the source and think, they also have no special logic in them, but to only propagate the records downstream. And basically, when executing this benchmarking application with each different serialization method, right? So here's the result we got. So here, this graph shows the throughput when executing this benchmark application. What we can observe from here is POJO gives the best performance in this case, right? Avro is not as fast as POJO, but still gives a better performance than cryo, and cryo gives the least performance in this example. It's also worth to mention that this benchmark result here, especially these numbers that's labeled on the right-hand side, this is very specific to sort of this benchmark setup, right? Your results may vary depending on, for example, what kind of record type you're using, what kind of Flink topology you are running with, as well as what kind of environment your application is running in, right? However, the general trend should be the same, where POJO is the most performant here. Avro is also, it's not as fast, but it's still better than cryo, and then cryo being a fallback is the slowest out of these three. So basically, what we want to show from this benchmarking application is, in our Flink application, we sort of want to stick with one of the efficient serializers, such as POJO or Avro, and try to stay away from using our custom-defined complex types that will need cryo to do the serialization for us. All right, so now we know that we want to stick with one of the efficient serializers, right? So the next question for us is, how can I find out what kind of serializers that my application is currently using, right? There's a couple of ways to do this. The most straightforward way is to use a flame graph in Flink, right? So flame graph is a very handy feature that comes out of box with Flink. What the flame graph tells us is basically what kind of functions that are currently consuming our CPU resources, as well as how much CPU resources it is consuming compared to other functions that's on your CPU. Flame graph can be accessed on your Flink UI. So basically, once you're in your Flink UI, if you click onto one of the operators, you will see basically a tab called flame graph here if it's enabled, right? Once you click into this tab, you will get a graph that looks like this, right, where we have lots of rows. Each row basically represents one function that's being executed on your CPU, right? So here in this specific example, as we can tell, there's lots of functions that's labeled as cryo there. So what this tells us is basically this specific example is using cryo to do the serialization for us. The other way to sort of ensure, you're using one of the efficient serializers is just to disable the cryo fallback, right? And you can do so by using this configuration here. It's called pipeline.generic types. You can set it to false to disable the cryo fallback. All right. Basically, with this configuration, what happens is if you set it to false, then your Flink application will throw an exception if cryo needs to be used anywhere in your application, right? And you can basically use this configuration to ensure that everywhere in your application is using one of the efficient serializers, and nothing goes through the cryo fallback. Right. So besides choosing the efficient serializers to do the serialization for us in our application, there are a couple of other approaches that we can take to also optimize the serializations in our application. One of the ways is to utilize task chaining as much as possible, right? Task chaining in our Flink application, it's basically an optimization in our Flink application. That means we're co-locating two operators together onto the same thread, right? And by doing so, we can avoid some serialization overhead as well as network overhead when we are passing records from operators to operators. In order for two operators to be chained together, there must be no repartitioning that's happening in between, right? So what that means is basically your operators need to have the same parallelism configured, and there must be no key bias or shuffling that's in between of your operators. So basically, if your operators are not chained together, if you click into your Flink UI and try to take a look of the topology, right, you will get a graph that looks more on the left-hand side here, where you have multiple boxes, right? Each box represents one operator here, and then these boxes are connected through some arrows in between. And these arrows are basically meaning when we're passing records from operator to operator, we're sort of doing serialization and then go through network and then deserialize them. However, if your operators are chained together, your Flink topology will look more to the graph on the right-hand side here, where you have like a single box. However, inside the single box, you actually have a chain of operations inside it, right? So here in this specific example, we have a single box. However, inside this box, we actually have three operators. We have a source operator, we have a map operator, we also have a sync operator inside it. All right, so besides utilizing task chaining, one of the other ways that we can use is to try to avoid unnecessary state accesses. Right? So like we discussed before, whenever operators are connected with RocksDB or whenever you are accessing RocksDB in your operator, there will be serializations that's happening in between, right? And if you're accessing your RocksDB, you can also potentially have a disk access by doing so. So basically, what we want to do here is to try to cache our state value as much as possible, and try to avoid doing unnecessary state accesses in our application to avoid the unnecessary serializations in between. All right, so that's basically everything in our first topic here, which is on serialization, right? So the next topic that we want to discuss is how to choose max parallelism, right? So let's begin by talk about what is max parallelism in our Flink application, right? So it is basically a configuration that you can set along with the configured parallelism of your operator. And what this configuration does is basically it sets the upper bound for dynamic scaling of the operator. And most importantly, it determines the number of key groups that we will have for state partitioning. So there's two ways that we can set max parallelism to our application. We can either set it for the entire program, which is a code snippet on the left-hand side there, or you can set it for like on a per operator basis, which is the code snippet on the right-hand side. So we mentioned our max parallelism determines the number of key groups that we will have in our state partitioning, right? Now you may wonder, what is a key group, right? So a key group is basically a collection of keys that will be assigned altogether to the same task slot when key bytes are executed, right? So to better understand how key groups are used in this process, let's first talk about what is key byte in our Flink application. How are key bytes executed, right? So in our application, if we're performing a key byte operation, right, what that does is it basically distributes records into sort of different task slots based on the key of the records. And when doing this, it makes sure that records with the same key will always be assigned to the same task slot, so that when we're doing some stateful processing in our operator, this makes sure that all the state associated with the same key will be available in the same task slot. Right, so for example, if we have a stream of records with keys 1 and 2 here, and if we're doing a key byte on them, basically what happens is all the records with key 1 will be assigned to the same task slot, and they will be processed there. Similarly, all the records with key 2 will also be assigned to the same task slot, and they will be processed there as well. So now we understand what key byte does in our Flink application, right? So let's actually take a look of how our key bytes executed, right? So what is going on under the hood when we're performing key bytes in our application? So the general process of key byte can be broken into three sort of steps here. The first step is to extract keys out of the input records we have. This is done by applying a user-provided key selector, right? So basically what happens is when you call key byte in your application, the API will ask for a key selector, which will then be used to instruct Flink on how keys are being extracted from the records. Once we get the keys for these records, the next step is to map keys to key groups. This process is done by applying this function here. It's on the right side. So we apply murmur hash to the hash code of the key, and from there we basically mod the configured max parallelism of that operator. Right, so here, since we're doing a modular operation to the configured max parallelism, what this tells us is basically the number of key groups that we will have is going to equal to the configured max parallelism for that operator. Once we have all the different key groups, the next step and the final step here is to assign these key groups to different task slots. Here, the number of task slots is going to be determined by the configured parallelism for that operator. So for example, if our operator is configured to have a parallelism of 4, we will have 4 task slots here that can process records concurrently. And the process of how key groups are assigned to task slots is done by applying this function that's That's like on the bottom here, where we take the key group ID, multiply with the configured parallelism of the operator, then divided by the configured max parallelism of the operator. Right, so this is basically the end-to-end process of how records are assigned to different task slots when key bytes are executed in our application. And basically, the takeaway from this process is that first, our configured parallelism determines the number of task slots we have for an operator. And then second, the configured max parallelism determines the number of key groups that will be distributed to the task slot we have. Right, so now the question is, how will key groups actually affect the execution of our application? Right, so here, let's take a look of this simple example here. Right, so let's assume we have an operator that's configured to have max parallelism of 6, and it's configured to have the parallelism of 4. Right. So from the previous slides, we know that number of max parallelism determines the number of key groups that we will have. Right. So in this case, we will have 6 key groups that needs to be assigned to the task slots, and they are with index 0 to 5. And we also know that the configured parallelism determines the number of task slots we have. Right. So here we will have 4 task slots with index 0 to 3. Also from the previous slide, we know that key groups are assigned to task slots by applying this sort of function on the bottom of the slide here, where the task slot index for your key group is calculated as the key group index times the configured parallelism divided by the configured max parallelism. Right, so let's actually follow this process by hand and take a look how key groups are assigned to these task slots and what kind of distribution we will get after it. Right, so let's start by processing the first key group, which is key group 0. Right, so the task slot index for our key group 0 is going to equal to the key group index times, which is 0, right, times the configured parallelism, which is 4, divided by the configured max parallelism, which is 6. Right, so 0 times 4 divided by 6 is going to equal to 0 in this case. Right, so that basically means our key group 0 will be assigned to task slot 0. Similarly, we can do the same thing for our key group 1. Right, so here the task slot index for key group 1 is calculated as the key group index, which is 1 in this case, times the configured parallelism, which is 4, divided by the configured max parallelism, which is 6. Right, so 1 times 4 divided by 6, and in this case, we're doing integer divisions here, so that will give us 0. Right, so basically, our key group 1 is going to be assigned to task slot 0 again. Similarly, we can do the same thing for key group 2. So task slot index of key group 2 is equal to the key group index 2 times the configured parallelism, which is 4, divided by configured max parallelism, which is 6. Right, so 2 times 4 divided by 6, doing integer division, in this case, will give us 1. Right, so this basically means our key group 2 will be assigned to task slot 1. Basically, if we keep sort of following this process and doing this operation for the rest of key groups we have, we will end up with a distribution that looks like this. Right? So what we can observe from this distribution is our key groups are not evenly distributed to the task slots we have. Right? So in fact, in this case, our task slot 0 and task slot 2 are assigned 100% more key groups than our task slot 1 and 3. Right? Assuming our keys are evenly distributed to the key groups, this basically means our task slot 0 and 2 is basically processing 100% more workload than our task slot 1 and 3. Right? And this could potentially slow down the execution of our application and also potentially cause some resource waste on task slot 1 and 3. Right, so what can we do in this case, right? So how can we sort of make sure we have an even distribution of key groups to task slots? Basically, what we want to do is we want to have our number of key groups to be a multiple of our number of task slots in order to evenly distribute them into these task slots, right? So in other words, the configured max parallelism needs to be a multiple of the configured parallelism for an operator in order to evenly distribute the key groups to task slots. So the general advice here is to set your max parallelism to be 5 to 10 times the configured parallelism of your operator. We actually learned this advice from previous year's conference talks, and we're actually following this advice in most of our production applications. And so far, this sort of advice here has been giving us a pretty good key to task manager distributions. However, there are a couple of sort of things we need to be cautious about when choosing max parallelism for our application. The first one is we don't want to set max parallelism to be a number that's too large, and there are internal overhead that's associated with maintaining these key groups. So if you set it to be a number that's too large, this will potentially bring some performance penalties to our applications. Also, changing the configured max parallelism of the operator will make our save point incompatible. Right? So what this means is basically your application won't be able to start from the previous save point if your configured parallelism is changed in your application. We're actually going to talk more on save points and how we're dealing with these incompatible save points in our next topic, which is how we are utilizing save points in our day-to-day operations to maintain our Flink applications, right? So again, let's begin by talking about what is a save point, right? So a save point is basically an image that captures the current progress of your Flink application. It is basically a snapshot in time of your application that stores things like your Flink state, your timers, and stuff like your Kafka offsets for the sources and sinks. Right? And you can basically use these snapshots to start your Flink application from some previous progress. There's a couple of use cases for using this. You can use it to pause and resume your streaming applications. You can use it to roll out code changes, which often involves application restarts. You can also use it to upgrade your Flink versions when the time comes. Save points are actually super important to us. The reason is that our pricing pipelines, they're actually stateful streaming pipelines, right? So we save lots of stuff in our state. Our state includes information such as market data information, reference data information, and most importantly, we have model parameters that takes a long time to rebuild if we're starting our application from scratch, right? So this makes losing state catastrophic in our production applications. And we definitely cannot lose any state in our production applications. However, in the meantime, we also need to support regular product enhancement as well as regular maintenance to our applications as well as the machines, which often involves restarting of our applications. Right? So whenever we need to restart our application but not losing any progress, this is the process that we take. Right? So assuming we have a running instance of a Flink application, and when we need to restart it, let's say to roll out some code updates, we first will take a save point from the application. And the save point will then be stored to some external storage, which in our case, we store it to our HDFS cluster. From there, once the save point is complete, we can then stop the streaming application. From there, we can roll out the code updates that we want to do. And then once the rollout is completed, we can restart the application from the save point that we just took so that when we restart it, it starts from basically where it left off and all the states and the progress is being picked up. The sort of biggest challenge with this maintenance sort of cycle here is save points are not always compatible with our code updates, right? And so far, we've had two main causes that gives us incompatible save points. The first one is incompatible data type updates. Right? So what this is basically when we need to make backward incompatible changes to the record type schema that we use in our Flink application. The other one is what we discussed previously, changes to the max parallelism. Right? So in our application, we actually often change this parameter together with the configured parallelism of the operator to ensure even distributions of key groups to task slots. Right? So what can we do in this case, right? So how can we sort of deal with incompatible save points without losing any of the data we have? Well, luckily, Flink provides a very powerful tool called the state processor API, right? So the state processor API is basically a powerful tool that allows us to read and write Flink save points. It provides us access to key state as well as operator state in our Flink save points. It is also relatively easy to learn since it's using the same data stream API that we use to construct our regular Flink applications. So far we've had 4 use cases for using state processor API. The first one is to restore from incompatible save points, right? So here, let's assume we have a Flink application that we want to make a backward incompatible change, right? So the process looks like this, right? So we first start by stop this application with a save point. We will basically take a save point of the application. The save point will be stored to some external storage. Again, in our case, we store them onto our HDFS cluster. From there, once we have a save point in HDFS, we can then use state processor API to sort of parse this save point and read the state out of it. Once we have the states from this save point, we can then apply the same changes that we need to apply to the application, right? So these are either state type changes or max parallelism changes. Once the changes has been applied, we can now write the save points back to HDFS. So on HDFS, we now have a sort of newly generated save point. From there, we can do the normal code rollout that we want to do. We can roll out the code updates, and then we can start this new Flink application from this generated save point, right? So now this generated save point should be compatible with our new Flink application, since the same changes has been applied to both the save point and the application itself. Sometimes we want to bootstrap state from external storage, right? So sometimes when we build a new Flink application, we don't necessarily want to start it from scratch, right? Perhaps we want to start it from some pre-populated progress. The state processor API can also help us to do this. So the process is very similar to our previous use case, where we use the state processor API to first read in the states. So basically now, instead of reading the states from a previous save point, we can now access a sort of external database and then read the states from the external database. From there, we can apply some transformations and we can save these states to our Flink state. Once everything is stored in our Flink state, we can now write this save point back to HDFS. So we will end up with a generated save point on our HDFS cluster. From there, we can start our new Flink application from this generated save point, so that this application is going to pick up all the state that we pre-populated with in our save points. Sometimes we also want to merge save points or merge Flink applications. So we've had a couple of times where we decide to merge multiple smaller Flink application instances into a single one to ease some maintenance, right? The state processor API can also help us to do this. The process is basically we first stop these sort of different smaller instances of the Flink applications. Each of them will generate a save point and will store it onto our HDFS cluster. From there, we can use state processor API to read in these save points on the same run, right? So what this will end up with is basically we will have multiple source operators in our state processor API. Once all the states are read in, we can now union these data streams to a single data stream. And then once the union is done, we can write this as a single save point back to HDFS. Right? So now we can basically start our Flink application, start like actually a single instance of the Flink application from this generated save point, so that it's basically taking all the progress from these smaller applications that we have before. Similar to merging save points or merging applications, we can also split it, right? So there are also times where we found out one Flink application is doing too much logic there. and we try to split it into multiple different ones. And we can do this using state processor API as well. The process is basically the exact opposite of when we are merging it. So now we will stop a single Flink application with SavePoint. So we will have one sort of large SavePoint in our HDFS. We then use state processor API to read states out of this SavePoint. From there, we can split this. From there, we can split the state that we're reading to multiple different data streams, perhaps by applying some filtering or some other changes. Right? And then we can basically write each of the data stream as a single SavePoint back to HDFS. From there, we can start multiple instances of our Flink application. And each of them will take one of the generated SavePoint that we have. And basically, what that means is each of these smaller Flink applications will take part of the responsibility from the previous Flink application that we have. Right, so these are basically the 4 use cases that we had with state processor API. With that, that is everything that I have for today. Thanks everyone for joining this session.